picking up good vibrations.
Now, let us compute the A case for a given example. It's the same example as we've done before. It's this rectangular wave. And before we started computing B1, B2, B3, etc., C1, C2, C3 were all 0. But we started doing that analytically, and it didn't seem to be very easy to get an expression for the formulas for B case. We can arrive at a very simple expression now with this new representation of the complex exponential with the A case. And there's also a formula for the A case, and that formula is very easy to be derived. We know that the A case are nothing more than the B case minus JC case over 2. Here's the formula for the B case and C case. If we simply replace these formulas here in the A case, we'll see that the factor 2 will cancel out. And then we can also group the two integrals into one, and let's see what we get. We get AK equals 1 over capital T, the integral from 0 to capital T of xt. Now we get this term from the BK, cosine of 2 pi over capital T kt. And then we get minus j times this term from the C case. dt. If you look here, this is nothing more than the exponential of minus j 2 pi over capital T k t. And so we can have this general expression for the AK, so we can compute it with just one formula. We don't need to rely on the B case and C case. We can just apply the following formula. It's a very simple and elegant formula. 1 over capital T, the integral from 0 to capital T of xt exponential of minus j 2 pi over capital T k t dt. Now we know that just pretty much like with the B case and C case, we can also apply this formula, or instead of considering the periods from one period from 0 to capital T, we can consider any period that we want. And in this case, it will make our life easier if we consider the period from one period from minus capital T over 2 until capital T over 2. So we get that AK is 1 over capital T, the integral from minus capital T over 2 till capital T over 2 of the signal exponential of minus j 2 pi of capital T kt dt. Now the signal is 0 outside in a period, is 0 from minus capital T over 2 until capital T over 2, is 0 outside of the integral from minus capital T1 until capital T1. So I can replace this limits of integration by this ones here, from minus capital T1 until capital T1 of x of t, which is 1 in this integral, times exponential of minus j 2 pi or capital T kt dt. Now the primitive of e to the power of alpha t is 1 over alpha e to the power of alpha t, also if alpha is complex. And so we end up with 1 over capital T e to the power of, so we have to divide by minus j 2 pi over capital T k. And here we have the same function, but we have to evaluate it when t is t1 and minus t1. So now this capital T will cancel with capital T. And I'm going to write this like this. 1 over pi times k. And I'm going to keep the 2j here, or the minus 2j here. And I'm going to evaluate, as I said, this function in these two boundaries, limits of integration. And this will give me e to the power minus j two pi over capital T k t1 minus e to the power of minus j 2 pi over capital T. This is a plus because I get a minus and a minus t1. Now, if we look at this term, we have here, I can replace this by a plus here, and minus here. We have e to the power of j something minus e to the power of minus j something over 2j. And that is equal to sine of that something. So we end up with 1 over pi k sine of this argument here. 2 pi over capital T k t1. This is assuming that k is different from 0. When k equals 0, it's also very easy to compute this. We have a naught. We already computed this, but we can do this again. It's 1 over capital T, the integral from 0 to, or from minus t over 2, capital T over 2, of x of t exponential of 0, which is 1, so we don't need to take it into account. The limits of integration, we can change them to minus capital T1 and capital T1, because the signal is 0 outside of this interval. The function there is 1, so we end up with 2 capital T1 over capital T, and we are done.